Hi everyone. Today I want to walk through a really interesting approach to clustering incomplete datasets. Specifically, how we can do k-means when some of our features are missing and still get meaningful clusters. The work I'm presenting is based on a 2024 paper and I've summarized the main idea, experiments, and why it matters in practice. So, what is the problem that we are dealing with? Missing data is almost normal for real world dataset. It happens because sensors fail, people skip questions, some values are removed for privacy, or we just don't capture everything. Traditional k-means can't handle missing values directly. If you just drop rows, you lose signal. If you impute before clustering, you alter the shape of your data before the algorithm even runs. So missing values can break k-means in ways that are not obvious. Let's look at how k-mean is usually applied. Step 1 is impute missing values. That means to that might be a mean fill, a median fill, or something more advanced. Step 2 is to run k-means using Euclidean distance. It looks clean, but here's the problem. The imputation step changes your distribution. If features are correlated, that bias spread across dimensions. So your clusters are man-made versions of your data and not the real thing. Why the geometry matters. K-means with Euclidean distance assumes clusters are spherical. That means the algorithm thinks that the distance in every direction costs the same. Real clusters are rarely spherical. In medical data, in financial data, in sensor data, features often move together. That creates elliptical shapes in feature space, and Euclidean distance misjudges how far points are from the cluster center. So, even if you impute perfectly, the distance metric itself works against you. So, what's your alternative? Mahalanobis distance. Think of Mahalanobis as Euclidean distance that is aware of covariance. If two clusters are if two features are correlated, the distance in that direction is cheaper because it's expected. It efficiently rotates and scales the axis so that the cluster shape matters. This allows k-means to discover elliptical clusters cleanly instead of forcing everything into a round shape. The paper's idea is simple and elegant. Instead of doing imputation first and clustering second, we do both together in a single loop. Missing values are inferred using the current cluster estimate. Clusters are updated using the cluster inferred values. So each step helps the other. Better clusters lead to better imputation, and better imputation leads to better clusters. This unified approach avoids committing to fake numbers upfront. So, what does the algorithm look like? The loop looks a lot like k-means. You start with an initialization, then assign points using Mahalanobis distance, then update the cluster centers and covariant metrics. At each iteration, you infer the missing values for each point based on the cluster parameters. We then repeat until the assignments don't change anymore. So it's not much more complex to understand. You're just optimizing missing values alongside labels. Here's a simple example with synthetic data. We generate two electrical clusters in 2D, randomly remove some values, and compare three methods. Impute K means unified approach with Euclidean distance and unified approach with Mahalanobis distance. You can see the unified Mahalanobis approach recovers the actual structure much more. Imputation plus k-means bends boundaries in weird ways because the missing values are filled without cluster knowledge. To evaluate this approach, the paper uses two common clustering metrics: adjusted RAD index or ARI, which measures how aligned our clusters alignments are with the true labels, correcting for chance matching, and normalized mutual information or NMI, which measures how much information the cluster label share with the true labels. Both metrics are good for synthetic data, but ground truth is known. The experiment used both synthetic data up to 10 elliptical clusters and classic IRS dataset with missing values introduced artificially, and they compared three approaches: impute plus k-means, unified with Euclidean distance, and unified with Mahalanobis distance. Here is a result summary. The results are pretty consistent. The unified Mahalanobis approach performs the best, higher ARI and higher NMI across different experiments. Unified Euclidean distance does better than impute plus k-means, but not by a lot. And the worst is the impute first approach, especially as missingness increase. The exact numbers depend on noise and the shape of cluster, but the direction is always the same. So, why is this even working? Two things are happening at the same time. Missing values are inferred, and the cluster and missing values are inferred inside the cluster center structure based on the mean and covariance. Distance respects correlation between features. This combination gives a truer picture of the dataset geometry. Instead of guessing missing values blindly, we infer them in context. So, in this slide, we present the list of references. The paper I summarized is from November 2024, and I have include the classic K means paper and Mahalanobis distance reference as well if you want the context. Thank you.